Hello, class. Coming to you today with section 4.2 in our 1530 class, Intro to Statistics Online. So we're going to be looking at 4.2. I'm going to start with sharing my screen. Okay, so remember in 4.1, we were talking about normal distributions. We examined the standard normal distribution, and then we looked at just any normal distribution with some random variable x and some given mean and standard deviation. Okay, so in this section, we're still going to be looking at normal distributions, but we're going to be looking at them looking at normal distributions for sampling means. So we tend to call it a sample or sampling distribution of x. All right, so let me kind of give you a little background so you get what I'm saying here. So when we think about the normal distribution, the bell-shaped curve, we're talking about the entire population for some random variable x is normally distributed. So this would be basically what your standard bell-shaped curve would look like for any normal distribution. Okay. Of course, more than half of your data will lie within one standard deviation of the mean, one below, one above. Almost all lies within two, and then right at all, or just about all, 99.3% lies within three deviations. So suppose this entire curve represents your population. Well, and it's normally distributed. Well, suppose instead of the entire population, which is usually highly unlikely that you have access to, suppose instead you are dealing with a sample, okay? A sample taken, let's say, from this normal distribution, from this population that is normally distributed. So if you were to take a sample, any sample of however big, typically 30 or more, but any sample, those smaller subsets will still be normally distributed. So what that means is, notice that the outside curve represents the whole population. Those inside curves here, those subsets, those smaller samples from that population peak at that same area, peak at that same value mean. So what that means is, when you're dealing with a population that is normally distributed, or if your sample size that you pull from the population is big enough, at least 30, then you will have automatically the same mean for those samples, for those smaller subsets. So when we're dealing with the sample distribution, we're dealing with a sampling distribution of X bar. Okay? A couple of things will always be true for this sampling distribution of X bar. As long as your original population is normal, then any sample taken will be normal. Or let's say the original population has an unknown distribution. As long as your sample is at least 30, you can assume normal approximation. So regardless of either case, the sampling distribution of X bar will have a mean mu for X bar equal to the original mean mu of the population. They will be the same. So whatever you were given for the entire population, that sampling distribution for X bar has that same mean mu value. Now, for the standard deviation for that sample, it will be equal to the original standard deviation divided by the square root of the sample size. So what does that mean? Well, remember the original standard deviation for a population, which is sigma here, it represents the spread of the data, okay? It represents the spread, or how far the data ranges from the mean. If you're only dealing with the sample, it should make sense, I hope, that your sample will have less spread. And it has less spread because the original deviation, the original spread, is divided by the square root of the sample size. So when we divide by that square root of n, we are reducing the standard deviation for the samples. Okay? So just remember that this is the only thing that changes from 4.1 to 4.2. Your mean for X bar will be the same as the original population mean, but your standard deviation for X bar will be reduced. It will be the original standard deviation divided by the square root of n. Okay? All right, so mean mu sub x will equal the same population mean mu, which is 70. Okay, because we're told that the population, this is for number 2, we're told that a population has a mean mu of 70 and a standard deviation of 14. The question says, find the mean and standard deviation of a sampling distribution of sample means, which just means sample means, we're talking about X bar. Okay, find the mean and standard deviation of a sampling distribution of X bar with a sample size of n equals 49. So that means mu sub x is 70, and that means sigma sub x will be the original sigma 14 divided by the square root of n, which is 49. And of course, we're going to simplify that. This may simplify to a whole number. It may simplify to a decimal. Just round accordingly. If you have a decimal, they'll actually tell you how many decimal places to round to. In this case, we're probably going to get a whole number here. So 14 divided by the square root of 49, which is just 7. So 14 divided by 7 is 2. So the standard deviation for X bar, the standard deviation for the sample means is 2. The mean for the sample distribution, for the sampling distribution, is 70. Okay? And we didn't calculate probability here just yet. We're just looking at the basics of a sample distribution for number 2. Okay? I think we actually get to calculate some probability here on number 4. So number 4, it says the population mean and standard deviation are given below. Find the required probability and determine whether the given sample mean will be considered unusual. Okay? For a probability value to be considered unusual, it would typically need to be outside of the range of 2 deviations from the mean, which means if you're talking about the actual value, it's probably less than 0.05. Okay? So if you're actually calculating the value, it's the probability value, in order for it to be considered unusual, it's less than 5% or less than 0.05. That's what makes it unusual, okay? So in other words, we're going to be calculating the probability here. So we're told that we have a sample of size 65, n is 65, and we want to find the probability of a sample mean, find the probability of X bar. Remember, the sample mean is called X bar. Has been called X bars all the way back since module 2. Sample mean is X bar. So we're looking for the probability of X bar being less than 23.2. That's what we're going to write as a probability statement. So probability that X bar is less than 23.2. Okay? All right. And we're told also and this is find this probability if the mean is 23, I'm gonna just circle these, and the original standard deviation is 1.22. So these are the original population values, population parameters. The mean of the population is 23, the standard deviation for the population is 1.22. And using that, and using our sample size, we want to calculate the probability that X bar is less than 23.2. Okay, so we're talking about a sampling distribution for X bar. And because we're talking about X bar instead of just X, because remember back in 4.1, this would have just been probability of X, but here is X bar. So we're talking about a sampling distribution of X bar. And when this is the case, mu sub X bar equals the original mean mu, which is 23. And sigma sub X bar equals the original sigma divided by the square root of n, which is 1.22 over the square root of 65. Now, that's going to be a decimal, and I'm going to go ahead and get the decimal form. And so that my answer, because this isn't my final answer, I have to actually calculate the probability. So I'm going to try to use at least 4 decimal places here, because that's going to make my probability that I calculate, because it's going to use this, it's going to make it more accurate. So I would say always go, when this is not a whole number, round to at least 3 or 4 decimal places. So 1.22 divided by the square root of 65. So we get 0.1513. Okay, 0.1513. All right, now let's calculate this probability. So I'm going to rewrite the probability statement. Probability that X bar is less than 23.2. That's what I want to find. So I'm going to draw my bell-shaped curve, because remember, anytime I'm looking for a probability for a normal distribution, that bell-shaped curve, that drawing, helps me to identify, when using the calculator especially, helps me to identify the region that I'm trying to calculate the probability of. Because remember, you need your lower bound, your upper bound. Okay, that's important. So here at the center is my mean mu sub x, which is 23. And I'm going to label this picture with this probability statement. So I'm looking for the probability that X bar is less than 23.2. Well, if I take this value, 23.2, it's slightly bigger than 23, so I'm going to put it over here to the right somewhere. And I'm just going to say 23.2. And I want the probability that X bar is less than that, so that means I'm shading to the left. So less than, shade left. Okay, so there's my shaded region. And when I shade to the left, I am shading to this tail end, all the way to this left tail end, approaching negative infinity. Okay, so my probability statement, probability that X bar is less than 23.2, is going to equal normal CDF, because I'm going to use normal CDF. Remember to get the area under the bell-shaped curve. When using the calculator, we use normal CDF, normal cumulative distribution function, because we're talking about this cumulative area under the curve. All right. I have to tell the calculator what my lower bound is. Remember, the lower bound is your left bound. So what's shaded here, or what's on the left side bounding this shaded region, and that would be negative infinity. And I use negative 999 to represent negative infinity. So that's my lower bound. Then I have my upper bound, which is the 23.2, the value from the probability statement, 23.2. Then I've got my mean, which is 23. My mean mu sub x. And then I've got my sigma sub x, which is 0.1513. So I want you to notice the only thing that changed from 4.1 to this section, or in this section, is the value of the standard deviation. The way we set up the problem is the same. The only thing that changed is the value of the standard deviation. And it's changed because when you're dealing with a sample, which is a smaller subset of a population, you won't have as much spread. Your standard deviation is the spread. It will be reduced because you have a sample of the whole population. Okay? So we're going to put that in our calculator. We press second vars, normal CDF. My lower bound is negative 99999. And make sure you use the negative sign and not the subtraction, because it'll tell you error. My upper bound is 23.2. My mean is 23. And my standard deviation is 0.1513. 1513. Okay. And it will paste that to my home screen, as you can see, written in the order that I have it, or it's typed here on my home screen in the same order that I have it here written. Press enter, and we get a probability of 0.9069. I'm going to round that 8 to a 9, because they typically want us to round to 4 decimal places. Yeah, it does ask for 4. So 0.9069. Okay, and I'm going to put that here, 0.9069. Then it says, would the given sample mean be considered unusual? Here, the sample mean would not be considered unusual. So right here, this is a drop-down blank. I think it has would and would not as your choices. So we would say would not be considered unusual, because that's a large probability, 90%, 0.90. So 90%. So that would not be an unusual outcome, because it has a probability that is greater than 5%. Remember, 5% is really, as a decimal, 0.05. Okay, so 0.9, a probability of 0.9 is way bigger than 0.05. So this would not be unusual because it has a probability that is greater than 5%. Okay, that is number 4. All right, let's see what else we have here in this section. All right, here's another one. We're finding the probability for some given sample mean. It says the population mean and standard deviation are given below. I'm going to circle. So the population mean and the standard deviation. So these are my parameters for my whole population. It says find the required probability and determine whether the given sample mean would be considered unusual. So for a sample of n equals 75, find the probability of a sample mean being greater than 214. So we have a sample size of 75. We want to find the probability of a sample mean, which is x bar, being greater than 214. So I'm translating that to a probability statement. So we want to find P, the probability that x bar is greater than 214. Okay. All right, so we've got to find our mean mu for x bar and our sigma for x bar. So our mean mu is 213 divided by the square root of n, which is the square root of 75. I'm sorry. Oh, goodness gracious. I'm totally wrong. That's the mean. I'm looking at deviation. Jumping ahead, I'm putting the answer here for deviation. The mean is just the same as the population mean, just 213. I apologize. Okay. Now we're into the deviation. Okay. Then that is the original deviation divided by the square root of n. So I'm jumbling it all together. I apologize. Okay. So the original deviation divided by the square root of the sample size. So that would be 3.7 over square root of 75. And we're going to, of course, round that to about 4 decimals. So let's take 3.7 and divide that by square root of 75. And we get 0.4272. If I go 4 decimals, 0.4272. Okay? So here's what I want to find the probability for, and here are my parameters for x bar. Let's draw a picture. Okay, so probability that x bar is greater than 214. Well, your mean is 213. So I'm going to put that at the center. 214 is a little bigger than that, so I'm going to put it to the right here. And we want the probability that x bar is greater than 214, so that means I'm shading to the right. Okay? And that means I'm shading out to this right tail end, which is approaching positive infinity. So when I find the probability that x bar is greater than 214, I'm going to use normal CDF. And I'm going to put in my lower bound, upper bound in the correct spots. Normal CDF. My lower bound is my left side bound. This region that's shaded is bounded on the left by 214. So lower bound is the left side bound. My upper bound is the right side, which is positive infinity. So I'm going to just put positive 99999. Okay, it's positive, so I do not use a negative there. And then my mu sub x is 213. My sigma sub x is 0.4272. Okay. So I've got second bars, normal CDF, 214, 9999, 213, and then 0.4272. And I hit paste. And it put the bounds and the mean and the deviation on my home screen. Press enter there. I've got 0.0096. Very small probability. 0.0096. Okay. So part here, the first part, the probability is 0.0096. Okay. Now, then it says, would the given sample mean be considered unusual? Yes, it's definitely unusual because look at the value of it. It's so small, the probability value was so small, it was less than 5%. But also, if you wanted to actually calculate it, you would say that 214 lies outside of the range of 2 deviations. If you were to, 2 deviations from that mean. If you were to take 213 and add the deviation and then add it again, you still would not reach 214. So let's do that. 213 plus 0.4272, and let's say plus 0.4272 again. I still get within or less than 214. I'm at 213.85. So what that tells me is 214 is greater than 2 deviations of the mean. It's beyond 2 deviations from the mean. So that means it is unusual. So the probability value showed that, as well as looking at how far this number, this parameter value, or this probability value that I'm trying to calculate for, how far it is from the mean, and it is greater than 2 deviations from the mean. So it is unusual. The sample mean would be considered unusual because it does not lie, okay, because it's outside of it. It does not lie within 2 deviations of the mean. It lies beyond 2 deviations. Okay, so it would be considered unusual. All right. Okay, let's see what else we've got here. All right, let's look at number 6. The population mean and standard deviation are given below. Find the indicated probability and determine whether a sample mean in the given range below will be considered unusual. If convenient, use technology to find the probability. So our sample size is 35, which is at least 30, so we automatically can assume normality. And we want to find the probability of a sample mean, X bar, being less than 12,749 or greater than 12,752. So we're trying to find the probability that X bar is less than 12,749 or the probability that X bar is greater than 12,752. That's what we want to find. So technically we're looking for 2 probabilities. And because it says or, we would find those or calculate those probabilities and then add them together to get the entire probability. So we're looking for the probability that X is less than that or greater than that, okay? So I will basically be finding each of these individually and then adding them together. So the probability that X bar is less than 12,749 plus the probability that X bar is greater than 12,752. And this is when mean mu is 12,749 and sigma is 1.9. So I'm going to draw my picture. My mean is 12,749. Okay, 12,749. And then I've got, and let me go ahead and put that as mu sub x, okay? Because remember, we have to calculate mu sub x, and it is the same as mu, which is 12,749, okay? And we also have to calculate sigma sub x, which is our sigma divided by n. And remember, n is 35. So this is the value that we're going to actually get a decimal for, because it's 1.9 divided by the square root of 35. So let's see what that is. And we get 0.3212. Let's go 4 decimals. 0.3212. Okay. All right. So I'm going to find each of these probabilities. I'm going to do them individually, and then I'll add them together. So this will be the first one. This will be normal CDF. I'm looking for the probability that x is less than 12,749. Well, 12,749 happens to be my mu sub x value too. And I want the probability that's less than that. Well, take that 12,749 is your mean. And it's at the very center. And it's cutting the bell-shaped curve into halves. So this shaded region is the left half of this. Remember, the total area under the bell-shaped curve is 1. So this must be 0.5. But we can verify that. The lower bound, because it's approaching negative infinity, the lower bound is negative 99999. The upper bound is the 12,749. 12,7, put that 7 in there, 49. And our mean is the 0.3212. Nope, I'm sorry. Our upper bound is the 12,749. Our mean is also the 12,749. Then we've got our deviation, 0.3212. So don't accidentally do what I was about to. You got to actually put that 12,749 in twice, because it's the upper bound as well as the mean. So lower bound, upper, mean, mu sub x, sigma sub x. Okay? So I'm going to calculate this first. And like I said, I already know it's a half because of the way that it's shaded. But let's verify. Normal CDF. So we've got 12,749. Nope, my lower is negative infinity, negative 99999. My upper is 12,749. My mean is 12,749. And my deviation is 0.3212. So my lower bound, just make sure you verify your values. My lower bound, my upper bound, my mean, my deviation. And again, yes, the upper and the mean match. They're the same. So I hit enter, and then to paste, 0.5. Okay? So this area is 0.5000. Now, let's look at the other one. Probability that x bar is greater than 12,752. Okay. Probability that x bar is greater than 12,752. So 12,752, well, that's bigger than the mean, so I'm going to put it over here to the right somewhere. Actually, I can go even farther with that if I wanted to. But your picture doesn't have to be perfect. But I'm going to go a little bit farther than that because it's not that big of an area. Not when your deviation is so small. That 12,752 means that's a really small little area. But your picture, again, doesn't have to be perfect. 12,752. Okay. And we're looking for the probability that x bar is greater than that. So that means we're shading to the right here. And that means we're shading out to this right tail end towards positive infinity. So this is the area we want to calculate now. We already know this area. We want this area now. And then we'll add them together, depending upon what they are. Normal CDF. The lower bound is the 12,752. The upper bound is the positive infinity. The mean is the 12,752. Mean mu sub x. and the deviation is 0.3212. Okay, so we'll put that all in our calculator. So we've got second VARS, normal CDF, 12752. Our upper, 99999. Our mean mu is still 12749. And our deviate, 12749. Oh my goodness, my goodness. 12749 is that mean. Ugh, don't do that. Okay. 12749, and then our deviation 0.3212, and then we hit paste. And there it is on our home screen. Press enter. Okay, let's talk about this, because I guarantee if you ever see this on your calculator, you're going to wonder, what is that? Okay, so understand that first off, probability is never bigger than 1. It's never more than 1. But every time a student sees this on their calculator, something like this with this little E text like this, they'll say the answer is like that actual whole number, when actually it's not. This E stands for scientific notation. So this 4.8966 E negative 21, that actually means, let me show you what that would look like if we were to write it out using scientific notation form. The calculator does a little shorthand. That would actually be 4.89 times 10 to the negative 21st power. That's scientific notation. The calculator uses E. When we write it, we actually write it as times base 10 to the negative 21st power. So this is 4.89 exponent E to the negative 21st power, okay? So what that means is if you were to write this out in an actual decimal number, an actual decimal approximation like this, you would be taking that decimal place and you would be moving it to the left 21 times. And in those empty spots, you would put in zeros. So imagine doing this, taking your decimal and moving it 21 spaces to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and continuing on. So all these movements, you've got empty spots, you would have zeros here. So you can imagine this is a tiny, tiny, tiny probability, almost so close to zero that we technically would say it's just zero. But it's tiny, tiny, tiny that the probability value is not even really something that you could calculate, that you would write out. With 21 zeros, that's just a zero probability. So when you add the two together, you get 0.5 and 0. Your answer is just 0.5. Because remember, the word or in probability translates to addition. So you would be finding this probability or this probability and adding them together. Since this probability was 0, the answer is just 0.5. Okay. Then it says, would the given sample mean be considered unusual? No, it wouldn't, because that is definitely greater than 0.05. That probability is greater than 0.05. So the sample mean would not be considered unusual because there is a probability greater than 0.05. So that answer, I was looking through the choices, the multiple choice, that answer would be D. The sample mean would not be considered unusual because there is a probability greater than 0.05 of the sample mean. So that would be D. The given probability is greater than 0.05, so it would not be considered unusual. Okay? All right. Let's take a look at this one. And here it says, use the central limit theorem to find the mean and standard error of the mean of sampling distribution. Okay, so when we're talking about the central limit theorem, we're talking about finding the mean for the sampling distribution of X bar. So we're looking for mean mu sub X, and we're looking for the standard error, which is another name for standard deviation, sigma sub X, okay? And then we'll look at the sketch of that. choosing the correct sketch. So it says the mean price of photo printers on a website is 226 with a standard deviation of 61. So this is for the entire population. The mean price is 226 with a standard deviation of 61. It says random samples of size 30 are drawn from this population. So we got N equals 30. So our sample size is big enough to where the central limit states when N is at least 30, we can assume normality. We can approximate normal, which means the mean mu sub x will equal the original population mean. Okay, so the mean of the distribution of sample means would also be 226. And the standard deviation, which is just another name for the standard error, or vice versa, the standard error is another name for standard deviation. The standard deviation for the sample mean would be the original deviation divided by the square root of n, which is 61 divided by the square root of 30. And it says round this to 3 decimals. So 61 divided by the square root of 30, we get 11.137 if we round that to 3 decimals. Okay. All right. So when we look at this sketch, here's what we're going to do. I'm going to create my own little sketch. That way then my graph, I just have to choose the correct one that it matches. So notice that you're at the center, at the peak of your curve should be your mean. That should be 226, your mean mu sub x. Now notice the little dots or the little tick marks to the right and to the left of the mean on these drawings represent 3 deviations above and 3 below. So 1, 2, 3 above, 1, 2, 3 below. And so I'm going to do that on mine. Now I'm going to actually write out what the numbers are, and that way we can then see which graph is correct. So 1 deviation above, this first value here, 1 deviation above the mean would be 226 plus 11.137. That's 1 above. 1 below would be 226 minus 11.137. Okay? And they don't have that first one above and below labeled, so I'm going to just keep on looking up further. The second one here, that would be 226 or above 2 deviations above 226. That would be 226 plus 2 times 11.137. And that just means 2 deviations above the mean. So I could add 11.137 twice, or I could say 226 plus 2 times 11.137. This one would be 2 deviations below it. So it would be 226 minus 2 times 11.137. And then lastly, this would be 3 deviations above it. So 226 plus 3 times 11.137. And this would be 3 deviations below. 226 minus 3 times 11.137. Okay. So because they're showing the third, 3 deviations above and 3 below, that's the one I need to make sure I calculate. Okay. And you can see the little markings indicate 1, 2, 3 above, 1, 2, 3 below. To the left is below, to the right is above. So I just need to see which of these numbers, which of these values would be correct. And I can already tell it has to be C. Your deviation is 11.37. No, I'm sorry, has to be D. Your deviation is 11.137. 409 is too large, okay? But let's just calculate just to be sure. Yeah, let's see. Maybe, maybe not. Let's see. Okay, so 226 plus 3 times 11.137. That is 259.4. And 3 deviations below would be 226 minus 3 times 11.137, which is 192.59. And that would technically go ahead and be probably 192.6. That's what I should have went ahead and put. Okay, so that has to be D. That is the picture of the correct sampling distribution with the mean and 3 deviations below it and 3 above it. So it would be D. Okay, and that's how you would calculate, because I think there are several of these. Maybe number 9 is just like this one. Okay, so there's one more that I want to look at, and it's number 10, and then I believe we'll be through with this section. So number 10, one more probability, finding probability. It says find the probability and interpret the results. If convenient, use technology. So of course we will. It says the population mean annual salary for environmental compliance specialists is about 66,500. So mean mu for a population, 66,500. Okay. It says a random sample of 31 specialists is drawn from this population. So N is 31. What is the probability that the mean salary, that X bar, of the sample is less than 62,000? So we want to find the probability that X bar is less than 62,000. That is what we want to find. Okay, so let's write that down here again and come up with our sample distribution parameters, our sample mean, our mean mu sub X, and our standard deviation sub X. And let's also draw a picture. So for the sample distribution, mean mu sub X is going to equal the original mean for the population, which is 66.5. All right. We're told here to assume that the population standard deviation is 6,500. So sigma sub X for the sample distribution is the original sigma divided by square root of n, which is 6,500 divided by square root of 31. N is 31. And I'm going to calculate that, get that decimal. 6,500 divided by square root of 31. We get 1,167.434. I'm going 3 decimals there instead of my usual 4. Okay, let's draw a picture so we can get our bounds. So here's our mean, which is 66.5. Okay, and we want to find the probability that X bar is less than 62. Well, 62, of course, is smaller than 66. So I'm putting it over here to the right, or sorry, to the left. And then I want the probability that X bar is less than that, so I'm also shading to the left. So it's smaller than the mean, so that's why I put it on the left. Okay, if it had been bigger, I would put it on the right. But where I shade is determined by the inequality. It's less than, probability X bar is less than 62,000. So less than means we shade left. Shade left. Okay. And so if we shade left, we are approaching negative infinity in this tail. So probability that X bar is less than 62,000 is normal CDF. Excuse me, normal CDF. My lower bound is the negative infinity. My upper bound is the 62,000. Excuse me. My mean mu sub X is 66.5. and my standard deviation is 1167.434. Okay, so normal CDF, second VARS, we've got a lower bound of negative 99999, an upper bound of 62,000, a mean mu of 66.5, a deviation of 1167.434. And we'll hit paste. And take a look at this. Another one of those E's. So this is 5 point, let's say we only write 2 decimals, 5 or 3. Yeah, 2 or 3. 0.5798. Let's go 3 there. And it says E -5. Then what that means is I would take that decimal and I would move it 5 places to the left because it's negative, because this is scientific notation. So to actually write it out in decimal notation or decimal notation, I would move my decimal 5 places to the left because it's negative. So 1, 2, 3, 4, 5. So my decimal is now here. And those empty spots, I've got zeros. I've got to fill them with zeros. So that is 0.00123. I need 1, 2, 3, 4 zeros. 0.005798. That is my probability. And the 0 in front of the decimal, you can put it in there if not, if you want. It doesn't matter. Just make sure you got the correct number of zeros after the decimal place. So that is a very small probability. Very, very small. So then it's asking us to interpret the results. Okay. Part A says about 1% of samples of 31 specialists will have a mean salary less than 62%. So they're changing these to percentages. Let's do that. Okay. So let me go ahead and round that off to this first significant digit. These are technically called the significant digits. Zeros are not significant. So I'm going to round this off to that first significant digit, and then I'll write it as a percent, because they are actually interpreting in terms of percentages. So this would be, still have those 4 zeros, 1, 2, 3. Actually, no, I'm going to round, since this is a 5, I'm going to make that 0, that first 0 here, a 1. Make that go up. So 1, 2, 3, and then a 1. So 3 zeros and a 1. Okay, and that's how they are rounding it. They are using percentages, but they technically did round that first. They used that first significant digit to round that 0 that's right beside it. So that's in decimal form. Okay, we want to write it as a percent, which means I take my decimal and I move it 2 places to the right. So 1, 2. So this would be 0.01%, because I will move my decimal 1, 2 places when I get ready to write as a percent. I have to move my decimal, okay? And technically it's still a decimal, but it's now in a percent form, okay? So now it says interpret the results. Well, we have only a 0.01%. So part B or part D is what we need to look at. Let's read part B. It says about 0.01% of samples of 31 specialists will have a mean salary less than $62,000. This is not an unusual event. Okay, part D. Only 0.01% of samples of 31 specialists will have a mean salary less than $62,000. This is an extremely unusual event. D is the correct answer. This is very unusual because it is less than 5%, extremely less than 5%. Okay, very, very small. So it is definitely unusual. All right, that is 4.2. Hopefully I cleared up any questions, anything that was concerning you or not quite as clear. I'll see you soon.